Yeah, we're doing integrals right now. We've been doing it for a little while. We started it at the very end of the last semester, and now we're more in depth on it.
Okay. So you're seeing that integral calculus is a lot harder than differential calculus.
Yes.
Differential calculus, we have all these nice little rules like the product rule, the quotient rule, the chain rule, the power rule. Integral calculus is a whole different animal.
Uh-huh.
So the way this normally works best is if you can verbalize problems to me, I'll write the problem and we'll solve it on my whiteboard together.
Mm-hmm.
If you can't, if it's a problem where, we need to be looking at a graph or something, then the best way to do that is for you to take a picture with your camera, your smartphone, and send it to my email address. And then we can bring that up as a resource to both look at.
What if it's like, because we're doing free responses, and they're like long, it's probably like, it's not a full paragraph, but it's a lot of words, and then there's like 5 parts to it. Would that be helpful if I send you a picture of that, so I don't have to read you like?
Probably, yeah, probably. Let me write my email on here. Send it to my email, not my phone.
All right.
1949 at gmail.com.
All right.
Do you have an Apple or a Droid?
I have a Windows phone. It's sort of crappy, but it'll send it to you real quick.
Okay.
It's really good.
Open up my email.
What was it again, David Cohen?
David Cowan, 1949 at gmail.com.
All right.
So in general, what are you working on right now? Just doing integrals using the power rule or by parts or?
We're working on things where it's like things, I don't know how to explain it, but they're sort of proportional to each other, like they sell this for this much, and so how much, like how many people can come in or something like that, I don't know.
Okay. But it's definitely, it's not related rates. That sounds like related rates, but.
Yeah, it might be related rates. We're using integrals to solve them.
Okay.
So
it might be integration as net change.
Yes, yes.
Okay. Okay.
That sounds more like it.
Uh-huh.
Did you get your email?
Yeah, here, I got it. Just a second. Let me open it up and bring it up. Yeah, this would have been hard to verbalize for sure. Let me just read it here for a moment.
All right.
What are you getting in calc right now? What's your grade?
Right now it dropped to an F after the last test, so it's not doing so good. And then I also have the answers on the backs of the page if you want to see those too.
Well, it's always nice to have answers for calculus problems because otherwise you don't really know whether you did it right. And sometimes if you can't figure out how to do it, you can look at the answer and possibly figure out how to do it. So it's almost a requirement to have the answers if you're going to get into calculus problems. All right, I got this figured out here. Chatfield definitely has challenging calculus courses. I've tutored a number of calculus students from Chatfield, and they always bring the hardest problems for sure.
Yep.
All right, so let's think about this for a moment here. So this 6 root x dollars per meter is a rate. Okay, so if we integrate that function, we're going to get the total cost from, in this case, 25 to 30 meters. Finding a profit on the sale of a 25-meter cable, all right. So the cost is going to be the integral of 6 root x dx from 0 to 25. Well, can you take that integral? Do you know how to evaluate that?
Yes, I got to take the antiderivative.
Okay, what's the antiderivative of 6 root x?
Would it be 6 over, I want to say...
The best way to do these is to rewrite them with exponents instead of radical signs. So once you rewrite it with an exponent like that, then it becomes easier to integrate, because just use the power rule on integration, which is add 1 to the exponent and divide by the new exponent.
Should be 6 divided by 3 halves, which would be...
First of all, I'm going to add the 3 halves. Dividing by 3 halves is the same as multiplying by 2/3, so it's 6 times 2/3 times x to the 3 halves, which is the same as 4x to the 3 halves, which we're going to evaluate from 0 to 25. Do you know how to do that?
So we plug in 25 first, and then we subtract when we plug in 0.
Yeah. Well, what is 25 to the 3 halves?
So the 3 halves would be the square root, should be 5, and then 5 cubed is 125.
So times 4 would be 500. So 500, and then of course minus the 0. When we plug in x equals 0, it's just going to be 0. So the evaluation of this thing is 500. Now, that is the cost to produce the portion of that cable that's 25 meters long. The profit, if we're looking for the profit, is defined to be the difference between the amount of money received by the company and their cost of producing it. So what did they receive for that 25-meter cable?
$500.
They got 120 per meter.
Per meter, yeah.
So multiply 120 times 25, and you get what they sold that cable for.
So $3,000.
$3,000. So they sold it for $3,000. They bought it for $500. Their profit was $2,500.
Alrighty.
Okay. Using correct units, explain the integral in the context of this problem from 25 to 30.
So just be the last 5 they sold? or something?
Now, remember, this is the cost of a length of cable. In other words, it's not a consistent cost. They sell it for a linear cost. They sell it for $120 per meter. But the cost of producing it depends on how long it is. It costs more to produce a short one than a long one. So this could be considered the cost of producing the additional cost of producing a 30-meter cable compared to a 25-meter cable is what that would equal, and it would be in dollars, not dollars per meter, but dollars. In other words, we figured out the cost for a 25-meter cable was $500. Well, to figure out what that would be, I could evaluate it from 25 to 30, and whatever the additional comes out to be, that would be the additional cost to make a 30-meter cable.
All right, so we'll just
to do it, there's a couple of ways to do it. I can just do the same exact integral and evaluate it from 25 to 30. Or there's actually an easier way to do it, because when I evaluate it from 25 to 30, I'm going to have to do the math. So why don't we evaluate it from 0 to 30 and then subtract off $500? Although, and they didn't actually ask to calculate that. They just said explain the meaning of it. And we actually did that. Okay? So we don't need to solve that. As long as we gave the meaning of it, it would be the additional cost to build a 30-meter cable over a 25-meter cable. C, write an expression involving an integral that represents his profit on the sale of a cable that is K meters long. Well, his profit before was $120 per meter. That's what they sold it for. Well, times X, that's what they're going to get, right? Minus the integral from 0 to K of 6 root X dx. In other words, there's the expression involving an integral that represents his profit on the sale of a cable that is K meters long. When it was 25 meters long, then it was 120 times 25 minus the integral from 0 to 25. If it's K meters long, then it's 120 times K. And it's going from 0 to K, not 25. And it's 6 root X dx. So that would be the answer. Without that 0. Find the maximum profit that Mighty can earn on the sale of one cable. Justify your answer. So clearly the cost to produce goes up as you lengthen the cable. In other words, we figured out that it costs $500 to make a 25-foot cable. That gave them a nice profit because they sold it for $3,000. So clearly, if the cost doesn't go up with a longer cable, the answer would be an infinitely long cable, right?
Yep.
So therefore, it must go up. it must get more expensive the longer the cable is. So the maximum profit Well, let's think about that for a moment. In other words, when K is 100, you're not going to get a profit anymore. And when it's 1,000, you're going to have a loss. Somewhere at some perfect number is the maximum profit. Well, if this is our profit function as a function of K, and it is, how do we find the maximum? From differential? Well, first we're going to have to take the derivative of this function and set it equal to 0. And try to solve it. Well,
so we try to find P prime of K?
Yeah. Well, what is it equal to? What's the derivative of 120 times K?
120.
What's the derivative of this thing? What's the derivative?
6.
Yeah, the derivative of the integral of a function is 6 root K. Automatically. So, in other words, the fundamental theorem of calculus says this, that if I want to take the derivative of f of x, and f of x is equal to the integral of some f of t, dt. So if I want to take the derivative of that, that dx from 0 to x, it's f of x is the answer. And that's basically what we did in this problem. So now we're going to set this to 0 and solve it. Well, if I take the 6k on the other side and divide both sides by 6, I get root k equals 20. Square both sides, k equals 400. 400 feet of cable must be their optimum length. And we could test that, I suppose, if we really were so inclined, to see what profit they do make on a 400-foot-long cable.
I hope it's more than the 500.
Well, it should be more than any other length.
Yeah.
In other words, it should be a greater profit than a 401-foot cable or a 450-foot length cable, and it should be a greater profit than a 399-foot length cable. There is an optimum length, and it's 400 according to this. Do you have your answers?
So it'll just be 400, right?
Yeah.
The maximum profit.
No. Excuse me. We didn't multiply this by 120. They get 100. It'd be a 400-foot length cable would give them the maximum profit. So we still have to multiply this by $120 per meter that they get. So it's going to be $50,000 is the answer. No, 48,000.
Yeah.
48,000 what it had?
Yep, I just did it. Yep.
Okay. Do we have the right expression for C? 120k minus the integral from 0 to k of 6 root x dx?
Mm-hmm. So to justify that, would it be just that since the where it equals 0, where the first derivative equals 0, that's the only critical point, and so
yeah, in other words, if I give you a function like this, and this function is defined somehow, and I say, where is the maximum part on that function between those two lines that I drew, between A and B? Where's the maximum on that function? Well, it's not that easy to figure out without calculus. What we know is that maximum occurs when the slope is 0 of the tangent line. So if we take the derivative of this function, set it equal to 0, we're going to solve for this point right here. So I'll know that at 400 is where that profit function is a maximum. Oh, we didn't even figure out the maximum profit right. Excuse me. We figured out, I didn't give you the right answer. 400 feet is K. So to figure out their profit, I have to substitute 400 back into here. So it's 48,000 minus the integral from 0 to 400 of 6 root x dx. Sorry about that. I forgot to go back to the profit function. The 48,000 was just what they receive on that 400-foot cable. They sell it for $120 a meter. So we still have to subtract out their cost to produce it, which was the integral from 0 to 400 of 6 root x dx. So I guess we could do that real quick. What was that answer if we're looking to verify an answer? It's going to be, let's see, this was 4x to the 3 halves evaluated from 0 to 400. Square root of 400 is 20. 20 cubed is 8 with 3 zeros. So it's 48,000 minus 8,000. 40,000 should be their profit.
Well, shouldn't we multiply 8,000 by 4?
I forgot to do that. Yes, 32,000. Excuse me. So 16,000 is their maximum profit. That's what you answer you should see in the back.
I'll check. Yep.
Okay. All right. You want to send me another page, or is it maybe other problems you could verbalize? Whatever's easy.
No, but it's just more of those things. It's long. So I already sent you one, I believe.
Yeah, I got a couple more here.
The first one was the answers, but the last one.
Okay. This one is the one you want to look at? This is that one. This is with the answers, I see.
Yep.
Let me take a quick look at it here. Okay, that's what we did. Everything so far we did properly. All right. So I want to open the second document. Whoops, was that it?
I think so. That's off.
Yeah, it is. It moved to something. Okay, yeah, we got it right now. All right. You gotta love these kind of problems.
Yeah.
I'm being a little facetious, but
Oh, yeah.
actually they're not that bad. Once you get the hang of doing them, they're not that bad at all. Make some room. This right here is, what is that?
I can't even tell. There's a hole in it. I assume it's just something of T.
The rate at which the difference, or the distance between the road and the edge is modeled, so that must be d of t, because it's a distance. Okay? Remember that that is a rate, so it's a derivative.
Mm-hmm.
Okay? So, in other words, if that's the rate that that distance moves, then I can figure out the total distance by integrating this function from some time to another time. That'll tell me the total amount of sand, or the sand that's being washed away, basically.
All right.
Edge of the water was 35 meters from the road when the storm began, and the storm lasted 5 hours. The derivative of the function is that's the derivative of that function. What was the distance between the road and the edge of the water at the end of the storm? If we want to know how much was washed away, we're going to take the integral of this function here. Not sure yet why they took the derivative of it, but we don't care. This is the rate at which the sand is being washed away. Or really, it's the rate at which the distance between the road and the edge of the water is changing. So if we want the total change during 5 hours, we're going to integrate this function from 0 to 5. And it'll give us the total change, the total distance that is changed.
Would we have to do 35 subtract that integral so then we can get the difference?
Well, we know it was 35 meters at the beginning of the storm. So whatever number we come up with, we're going to subtract from 35, and that's how close it'll be to the edge of the water at the end of the storm. Okay? So let's take the integral of this function. Integrated from 0 to 5, and that's basically how many feet or how many meters of sand will be washed away, right?
Yeah.
So let's blow this up and take the integral of it and evaluate it. How do I take the integral of that?
So you add 1 to the exponent and then divide by that. So you 2/3 t to the 3/2.
That handles
Plus,
that. What about this part?
Cosine is a negative sign or anything?
No, it's sine. Because the derivative of sine is cosine. The derivative of cosine is negative sine. So the integral of cosine, or the antiderivative of cosine, is sine.
Okay.
And then what about that part?
It's 3x minus 3x.
Minus 3t.
3t.
So I'm going to evaluate this whole thing. That's the integral from 0 to 5. Again, I can see that the 0 produces nothing but zeros. So if I evaluate it at 5, I'm going to have my answer.
Mm-hmm.
I don't like it already. Hold on a second. Let me think about this for just a minute. Why did they give us this derivative of that?
Mm-hmm.
Because up here, this function is a rate function. A rate, the rate at which the distance is changing. That means this is already a derivative function. And integral as net change is always about integrating a derivative function from some distance to another. And it'll give you the total amount. It's a variable amount. In other words, it doesn't wash away the sand equally every hour, otherwise it would be linear. So since it's not linear and not figure-outable without calculus, we need calculus to do it because it's a changing rate. Do you have the answers on this one?
Yeah, I sent you now, because on theirs, it just shows them overtaking the integral, but then they add 35 to it. Somehow it didn't really show what they're doing, but they added 35.
The reason I question my answer is because the 5 to the 3/2 is not a particularly nice number. But I guess we can work with it.
Well, I think we're allowed to use a calculator on this.
Okay. Because we're going to need a calculator to figure out the sine of 5.
Yeah, because I can just plug that function into my calculator and it'll give me...
Okay. Why don't you and come up with a number here for us?
Go of the function.
Make sure you're in radian mode.
All right.
It's one thing about calculus and trig functions. They don't work if you're in degrees. The derivative of the sine is only cosine if you're in radians. It's not all of these beautiful trig relationships in calculus. That's why they came up with radians, because they didn't work in degrees.
Yeah, I got it.
Does it agree with it agrees with the answer?
Yep.
Okay. Part B, using correct units, interpret the value of f prime of 4 being 1.007. First of all, the definition of f prime of t being the derivative. Derivatives are slopes. So f prime of t would be the slope at any point of this function. In fact, let me bring up Wolfram alpha here. I'm going to put this function into Wolfram alpha and then show you what I'm talking about. Are you familiar with this at all?
Nope.
This is a nifty program. Better than your calculator. Let's see, x raised to the 1/2 plus cosine x minus 3. Let's see what this curve looks like. Beauty of Wolfram Alpha is it, first of all, it gives you feedback on what you put in, so you know what you put in, whether it's right or not, which your calculator doesn't do. And can present a lot of problems. So here's what this curve looks like, the blue curve. The orange is the imaginary part. We're only caring about the blue part, the real part. So they gave us the derivative. If we're talking the derivative of this function, even if this is a derivative function, we can still take the derivative of it. And when we take the derivative of it, we're going to get the slope at any point in time. So when they said f prime of 4 equals 1.007, it means the slope evaluated at 4 is plus 1.007. And if you look at that curve and look at the slope of the tangent line right there, pretty close to 45 degree. In other words, the slope is going to be close to 1. And that's what they've said in their problem is that f prime is going to be the slope anywhere, but f prime evaluated at 4 is going to be specifically the slope of this function at 4. So they're saying the slope is 1.007. Interpret the value in terms of the distance between the road and the edge of the water. Well, let's have another look at this curve. So, if I want the amount that is eroded away in 5 hours, or the change in the amount that's eroded, the x-axis here is the time axis. So if I add up the area between this curve and the x-axis, I get the total amount of change in distance. This is a little bit strange because what this is kind of telling me is that the distance, there was no erosion starting here, and is this the right curve? Square root of x plus cosine t minus 3. This looks like negative. In other words, this
I said the answers.
What's the...
It says 4 hours after the storm began, the rate of change of the distance between the road and the edge of the water is increasing at the rate of 1.007 meters per hour squared.
Okay. Yeah, no, that makes sense. It's... Oh, you know what it is? It's the same relationship as velocity and acceleration. That's what it is. In other words, you're familiar with the position function, and then the first derivative of the position function is velocity, and then the first derivative of velocity is acceleration. And acceleration has the units feet per second squared. So, whereas velocity has the units feet per second. Well, this is very similar. In other words, this is the velocity function, the rate at which it's washing away the road. This is the rate of change of that. In other words, this would represent the acceleration of that rate. And so that's why when they take the first derivative of this function, we're essentially getting an acceleration function. And that's what your answer told you, is that at 4 hours, the rate at which the road is being washed away is changing at this rate.
Mm-hmm.
In the same way that a car would change its velocity from 40 miles an hour to 50 miles an hour by accelerating from 40 to 50. And you would have a function for that acceleration. At what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? Well, how do we want to...
So we have set the derivative equal to 0?
Yep. In other words, this is the derivative, so we set that equal to 0. I can do that real quick on my Wolfram Alpha here. One divided by x raised to the 0.5. Whoops, and there's a 2. Minus the sine of x equals 0. Happens in 2 places. Interesting. 0.2555 and 2.28. In other words, there are 2 places should have 2 answers for this one. Right at the start of the storm at 0.25 hours and then at the 2.28 hour mark.
I'm looking at the answers now. So that would be the 2 spots because it's got weird things on the answers. I believe.
What's it got for the answers?
It says f prime of t is equal to 0 when t equals 0.661 and 2.84. The minimum of f for 0 or t from 0 to 5 make it 0.661, 2.84, 3, or 5, and then they're evaluated f of 0, f of 0.661, f of 2.8, and then f of 5.
If I plot just this function, not as an equation, here's the derivative function. Here's my curve. So that's equal to 0 at these 2 spots, right there and right there. In fact, it gives you the zeros here. It's those same 2 numbers. How did they get a different answer than you got? Didn't they set f prime of t equal to 0?
Yep, and then it says when t equals 0.66187 and 2.
Notice my function's wrong. Here I was bragging about how it gives you the feedback, and this is not the function that we're looking at there. It's 1 over 2 root x.
Oh.
Yeah, I need parentheses right here. That's why I got the wrong answer. Yeah. And my zeros now are here and here, and that's your numbers, 0.6, 0.66 and 2.84.
Yep.
And what else did it say?
The minimum for f from 0 to 5 may occur at 0.661, 2.843, or 5. So it used the critical points and then the endpoints of the function, so 0 and 5. And then it looks like she evaluated f of the numbers.
So she needs f of both of those numbers, and then she needs f of 0 and f of 5.
Yep.
Okay. And whichever of those is the greatest, you choose that one.
Mm-hmm.
All right. Did it give a final answer? Which one is it?
It is f of 5.
I was going to say, if you look at this curve, f of 5, that's the highest point on that curve. Of course, this isn't the curve we're using to evaluate it. You're plugging in the zeros and the endpoints into this equation up here.
Mm-hmm.
And apparently f of 5 gives the biggest number, not f of 0.66, nor f of 2.84, nor f of 0.
Mm-hmm.
All right. After the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate. So that the distance between the road and the edge of the water was growing at, shouldn't it be decreasing? Oh no. No, if they're pumping sand back on, it's increasing. Okay. And P is the number of days since pumping began. Write an equation involving an integral whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water.
So then we just take, well, because we just figured out the integral of how long it takes for it to destroy itself. So then when we just do the opposite, so then we just negative that or something? Like negative the integral from 0 to 5 of the function?
Yeah, the integral, in other words, the amount of distance that was created was the integral of g of p is going to be the rebuilding, the amount of sand or the amount of distance added between the road and the edge. And like you said, we know the amount of distance that was lost in the 5 hours of the storm. So whatever that number was has to equal the integral of this from 0 to x, or 0 to p. Write an equation involving an integral expression whose solution would give the number of days that the sand must be pumped to restore the original distance. Well, that would be P. What was the number we came up with as to how much distance was eroded away in 5 hours?
The total distance that was eroded was 26.49 meters.
Was taken away?
Yeah.
So we subtracted that from the number 35 to get an answer to A?
Yeah, well that was the answer to that, yeah.
Well, actually it could be different. In other words, the answer to A was what number?
26.494.
Okay, now that means that approximately 9 meters were eroded away, right? Because it started at 35 feet. So, in other words, the question A was not how much was eroded away, but how far away is it from the edge of the water at the end of the storm?
Mm-hmm.
And the answer apparently is 26.49, which means 35 minus that is the amount of erosion that took place. So 35 feet is where it started. It ended up at 26 feet. So approximately 9 feet of erosion took place. We need to rebuild up 9 feet of sand, and we're going to do it by integrating g of p for p number of days until that's equal to 9. Now, we don't know how to solve this because they don't give us g of p, but they don't ask for a solution. They just said write an equation. So if I knew what g of p was, then I could solve for p.
The answer is I just flip back and now it says for D is just the negative integral from 0 to 5 of f of 2 dt is equal to the integral from 0 to x g of p dt.
Which is what we did. In other words, we got this 9 feet by taking the integral of the original function from 0 to 5.
Mm-hmm.
And we set it equal to the integral from 0 to p of gp dt.
Mm-hmm.
Okay?
All right.
It's 8 o'clock.
All right, good. That was it.
Okay, good. I hope I was helpful.
Yep.
These are pretty tough problems. But,
Yeah.
yeah, yeah, well, what can I say? If you need any more help, Matthew, let me know.
All right.
And you know how to schedule? You know how to go to
Yes.
you did the scheduling yourself? Okay.
No, but I watched my mom do it, so I know how.
Okay. All right. Let me know whenever you need help. Be happy to.
All right.
I love tutoring calculus, even when
All
it's
right.
okay. Talk to you later.
All right. Bye.
One thing. I did record this session.
right.
One of the advantages about online is that each session gets recorded. It takes me a few hours to process it. The file won't be ready until the morning, but I need to send you the link to watch it if you want to be able to. If you can give me your email address, I will write it on here. What is it?
ML dot period THOR Thor 1995 at yahoo.com.
I get that right? ml.thor.
Yep.
Thor
Yep.
9895. Okay. That's where I'll send it.
All right.
Okay, Matthew. Thank you.
All right. Thank you.
Bye-bye.